Greetings, welcome back to another video for this series where I solve 100 problems for 100 days. Um, First of all, I apologize for not being able to upload many videos. Recently, I was completing my semester and I really hate to give excuses, but I was quite busy. But fortunately, I realized that I was fortunate enough to qualify for the second round for KMO this year. So I'll be taking the test again this year, and this time I really want to do well because last year I didn't do quite well. So I'm planning to do this series again and maybe make more videos, complete the series first and make more videos about pre- preparation until November. Uh, so thank you for coming in, and let's get started with this problem. This problem is 2006 IMO Shortlist A5. And to be honest, I was like halfway there. So I didn't solve math problems for a while because I was studying for other stuffs. And this was like my warm-up problem, and obviously I couldn't solve it at first try. So uh, I'm going to explain how I solved the first half, and uh, I'll explain the other half from the official solution. So let ABC be the sides of a triangle, prove that this inequality is true. Now, the first thing that came to my mind is, oh, this inequality is homogeneous. Because even if we scale them, like let's take a look at this term. Let's scale them by t. So we get bt plus b ct minus at over square roots of bt plus root ct minus root at. This is equal to root t times root over root t root b plus root c minus root a. This two cancels out, and this leads us to our original term right here. So we know that this inequality is homogeneous, and because we know that, what we can do is normalization. That's one of the greatest techniques. I think that will help us a lot. So without loss of generality, because ABC, it just said they're the size of the triangle, and I'm pretty sure they just said that because they don't want this to be imaginary numbers. So without loss of generality, we'll log A is greater than or equal to B, greater than or equal to C, because they can be equal to each other, isosceles and equilateral triangles. And because normalization, because this inequality is homogeneous, we can set let n a plus b plus c equals 1. Now after this, what I wanted to do in my initial attempt was to prove why don't we just prove that this individual terms are less than or equal to 1. That way when we add, we get the entire inequality, entire left hand side less than or equal to 3. But that did work well for the first term, and let's do that because so let's substitute first. So we want to prove that lemma. Do we have to write lemma? Let's just write it because it's first half. I can't write today. Over root b plus root c minus root a is less than or equal to 1. Yes, I'm not going to write it formally because I think it will take up too much time and space. So here is our proof. because a plus b plus c equals 1, what we can do is we want to prove it suffices to show that root b plus c minus a is less than or equal to root b plus root c minus root a. And let's just continue from here. So we know b plus c equals 1 minus a, so we want to prove 1 minus 2a is less than or equal to root b plus root c minus root a. What I did from here is I moved this term to the left side and I squared them, because that way we can find, like, we can use a plus b plus c at 1. So we got minus 2a plus 2 root a times 1 minus 2a is less than or equal to b plus c plus root 2bc. Now this is very pretty because let's simplify this. A 1 minus 2a is less than or equal to, let's move a here, so a plus b plus c plus 2 times root bc. Now because we said a plus b plus c equals 1, we can cancel these terms. So in other words, it suffices to show that let's cancel 2 too. So it suffices to, and let's square them. So it suffices to show that this is true. Now this is actually pretty straightforward. I was like, oh, how should I continue? But the reason why this is quite straightforward is because we know 1 equals a plus b plus c. So substituting a plus b plus c, we get a plus b plus c minus 2a is b plus c minus a. And from here, we can just use the definition of bc. And what I mean by that is, let's move these terms. So it suffices to show it. We just have to show that a squared plus bc minus ab minus ca is greater than or equal to 0. Now, when we take a look at this term, we get b minus, we can factorize this to b minus a times b minus c. Oh, never mind, sorry. Yes, I felt something was wrong. So a minus b times a minus c. And because we said a is greater than or equal to b and b is greater than or equal to c without loss of generality, we know that this term is positive, this term is positive. In other words, a minus b times a minus c is greater than or equal to 0. So our first lemma is proven. I didn't make any mistakes, right? A squared bc, yes. Now, I actually wanted to use the same method to prove that these two terms are both less than or equal to 1, but I couldn't prove that because this didn't hold true. So, I mean, we didn't actually use like properties of this inequality in here. So let's just shift this and see if that works. BC minus AB. So this is what we will get, I think, when we do for the second term. But this doesn't work because b minus c times b minus a is actually, this is negative and this is positive, so this is less than or equal to 0, not greater than or equal to 0. So this doesn't work. So what we can do is set our second lemma. And this is the second half. I was stuck here and I looked at the solution, and what they did was, interestingly, they grouped this too. So they said c plus a minus b over root c plus root a minus root b plus, is a plus b, a b c over a plus root b minus root c is less than or equal to 2. Um, yes. So what we can do here is actually this is I don't know like how they put this off, but for me at least it wasn't really intuitive and it was actually hard to capture why we had to set this, but it works like magic. So let p equals root a plus root b, and q equals root a minus root b. So multiplying these two, we get a minus b equals pq. Now let's substitute this. So it suffices to show that c plus pq over root c plus q plus did I write something wrong? A c a minus b c a b c a b a b c. This should be right. Wait, did I make mistake in the first? No, I think no. This is right, and that's what I did. I think C A B. Oh, is it not A and B? Oh no, it is right. I think. Oh, B minus C. What? I'm sorry. Where did I make the mistake? Did I um A minus maybe wait maybe it wasn't A and B. Huh? Maybe maybe it was A and C instead. Maybe it was A and C. No, but the fact that this term, this is true because I remember the official solution using A and B, and unless I made a mistake here somewhere, this should all be right. A times A plus B, A squared minus AB minus AC. No, our first half is correct. That is what I did, and I remember using the first term. CAB ABC. CAB ABC. Interesting. Then we don't have to follow the official solution. Let's just try and change. Maybe my memory slipped. Maybe. Then what should we put as P? Let's say P equals should we center? We could either use a B and C or A and C. Oh, B and C. We could use B and C. Oh, let's use B and C because A is the greatest term and that might make our lives easier later. Root b plus root c, and q equals root b minus root c. Then naturally, like what we did, equals pq. Now let's substitute it. So we get c, no, not c, a minus pq, root c, no, not root c, root a minus q, plus root a plus b plus c, b minus, so a plus pq over root a plus q. So we need to prove that this is true. Now, this is where the genius part comes in. I don't know like how they thought of doing this, but they use Koch here, and the way they use Koch here is really interesting. So, just as a reminder, Koch-Swartz inequality, like using two terms, for variables, it states that it's less than or equal to a squared plus b squared times x squared plus y squared. Now here, a can be, I shouldn't have used a because we have a here. Let's use alpha then. Alpha and alpha, beta. No, beta. Let's say alpha equals root a minus pq over square roots of a minus q. And here x will be square roots of a minus q over 1. So what we can do here is we just need to prove that this whole thing squared is less than or equal to 4. Or squaring them, we can say this whole thing squared is less than or equal to 4. Or what we can do is alpha squared, which is a minus pq, over root a minus q, plus what is beta? Beta, it follows the same pattern, q over a plus pq times x and y, x squared and y squared, minus q over 1 plus root a plus q over 1 is, oops. So if we prove that this is true, so if we prove this inequality, then by Koch-Swartz inequality, this thing squared will be less than or equal to 4, and thus this thing is less than or equal to 2. So let's do it. Let's make common denominators first. So a minus q squared over, let's just do it here, plus aq minus pq root a. Oh no, I'm running out of space. And here, a root a plus pq root a minus aq minus pq squared times, and this thing is straightforward, a minus q squared, 2 root a is less than or equal to 4. Now this cancels out, so we get 2a root a minus 2pq squared over a minus q squared times a minus q squared over 2 root a is less than or equal to 4. Now, let's group them. So we get 4 times, because 2 times 2, root a. Let's take this first because it looks more clean, or cleaner. Q squared is less than or equal to 4. So what we need to show right now is, my writing is big, what we need to show right now is a squared minus 2pq squared a over a minus q squared is less than or equal to 1. Then this inequality will be true, this, that, and that. We can prove it. Now this is actually very interesting because what we need to show is if we show that this thing is less than or equal to a squared minus a squared minus 4q squared. If we prove that, then we know this is oh no, never mind. Sorry. If we prove that this is less than or equal to 2aq squared, then obviously this will be less than 2 minus 2aq squared plus q to the power of 4, and thus this thing will be less than or equal to 1. So we just need to prove this thing, or we need to prove pq squared root a is less than or equal to 2aq squared. Let's cancel these two and flip them. So p root a greater than or equal to a. So we just need to prove this. So we need to prove that p is greater than or equal to root a. And how should we do that? Well, p is greater than or equal to 2a. P is greater than or equal to p is this, right? So we need to prove if this is greater than or equal to. And we also note that a, b, c are the sides of the triangle. So let's square them. B plus c plus 2 root bc is greater than or equal to a. And obviously this is true because b plus c is greater than or equal to a. Greater than a by definition. So we just proved, we didn't formally prove it, but we proved that our lemma this is true. BCA, CAB, BCA, CAB, ABC, BCA, BCA. I think I can remember. So BCA, BCA. Oh, BCA. Okay. So by lemma 1 and 2, square root of b plus c minus a b plus root c minus root a plus root c plus ca minus b over c plus root a minus root b minus plus root abc plus b minus c root a plus root b minus root c is less than or equal to 3 because 1 plus 2 equals 3. And we just proved this problem. Please, yes, I think this problem is really interesting because the first thing that I think came into my mind and to most of us's mind is using normalization, because like this is very pretty inequality that they are homogeneous and BCA, BCA. But that didn't turn out to work well for the second half because of this condition. We have to set A is greater than or equal to B or greater than or equal to C so that we can prove the first lemma. But that actually didn't help for the second lemma if you're to use the same method. So using this weird but very magical substitution, I don't know like how they thought of this method. Now actually this is not what's written in the official solution. They use C, and like how they derive this one is quite different. I think they use the inequality, this one again, to prove it, but I might have made mistake. I'm pretty sure I didn't make here, but if I did, or please feel free to let me know in the comments. Uh, I might have made mistake when studying for this problem earlier. So I think this problem is really interesting in a way that they use cosh, like this is actually very magical. They use cosh in a way that is very unexpected. So I think overall this problem was really interesting and very a good problem to um, get back to studying for Math Olympiad again after like a 1 or 2 months of break. So because I will be solving more problems as I study for the test in November, I'll be making more videos like this. Please don't forget to share this video with your peers or anyone who loves math. And thank you for watching and see you in the next video.